So welcome back to the analysis seminar. Our speaker today is Fernando Lledó from Universidad Carlos III de Madrid and ICMAT, and his title today is Isospectral Graphs for the Discrete Magnetic Laplacian.
Okay, Jose, thank you very much for the invitation. And it was a quite improvised invitation a few weeks ago. And so let me apologize for the slides because, well, I prefer usually to speak on the block. Since this is an analysis seminar, the title seems quite combinatorial. And so let me say that this, what I'm going to present here, is a joint work with John Favila, now postdoc in Edinburgh, and Olaf Post, former friend and colleague now in Germany, at that time in Durham in England. And yeah, let me say that this project is part of something which is now, I tried to justify the name analysis. So this is part of something, a big field, which is called analysis on graphs. Or if you prefer, spectral graph theory, where you have a graph and you define operators on them, on the graph, and try to establish a relation between geometrical or combinatorial properties of the graph, phrased in terms of properties of the operators you define. So for combinatorialists, they like to use the adjacency matrix, which describes completely the combinatorial structure of the graph. But I will focus today on the Laplacian, on different kinds of Laplacians. And the reason, well, there are many reasons. The Laplacian carries more the geometrical structure of the graph. And the Laplacians also, they connect with really beautiful classical results like Weil asymptotic formula. For instance, if you have a bounded manifold in 2 or 3 dimensions, bounded manifold with boundary, then you can recover the volume of the manifold looking at the asymptotic eigenvalue distribution of the Laplacian with Dirichlet conditions. And also the classical and really well-known question of Kac that asks about if you can hear the shape of the drum. This refers to the eigenvalues of the Laplacian on a bounded planar domain. And so within this context, I like to focus on the what is called magnetic Laplacian. So the aim of my talk is what is the aim of my talk?
No. Un momento. Sí, vale. Ya se lo paso.
So the aim of my talk is in the next slide. Don't worry, it's a Friday seminar. I scheduled a short seminar. So don't be...
Sí. Un momento. Vale, ya lo he entendido. Si yo puedo tocar, tú no puedes.
Ah, here it is.
Prueba otra vez, dale otra vez.
No.
A ver, ahí está.
Okay, so now the aim of my talk, I'm going to speak about isospectral graphs, as I told you, for different families of Laplacians. Okay, and what I would like to convince you today is that the following flowers. So this is the first one. So this is the first graph. Is isospectral to that one and to that other strange flower. Okay, so these graphs are not isomorphic, and the reason is just the degree list. So if you put on the vertices, you collect all degrees. This degree list is an invariant and graph isomorphisms, because graph isomorphisms preserve the adjacency structure. And so here you have an edge of degree 1, which is not here and not here. So here you have an edge, a vertex of degree 2, which is not here and not here. So all the three are not isomorphic as graphs. And I will try to show that, or to convince you that these are isospectral, okay? And the family of Laplacians I'm going to analyze here are so-called magnetic Laplacians. So if you don't like magnetic fields, or if you like physics, that's you will accept it. For me, the magnetic field has many, many advantages. It serves as a kind of interpolating parameter between very important Laplacians. You will see in a minute what I mean. So these are isospectral for any discrete magnetic Laplacian. So it's a continuous family of Laplacians you can label with a magnetic field. Physically, you can think of a constant magnetic field going through the graph, and okay, so that's what I'm trying to explain. The fact that these graphs are isomorphic, and show you what is the geometrical reason. Then I will focus. We like to work with completely general weights on the vertices and the edges. But I will focus today, since this is a Friday seminar, on standard weights, which is the kind of weights that mathematical physicists use. Combinatorialists put a weight 1 on the vertices and 1 on the edges. So this would be the 1 and 1 would be the combinatorial weights, standard weights. They put, one puts here the degree as a weight of the vertex, okay? And what I'm going to present is a bit more general, but let me focus on these concrete weights. And as I told you, these are very, very useful in mathematical physics literature, discretizing important operators. So let me also say why I do this. Well, first of all, it is really much more difficult to compute isospectral graphs, or to construct isospectral graphs for standard weights than combinatorial. And there are these lists, you know, this by brute force, you can just compute all simple graphs with 1, 2, 3, 4, up to, I don't know how big the list is now. And then you compute all graphs, you compute by brute force all the spectra and decide how many are isospectral. For the combinatorial weights, with 9 vertices, this is 15% isospectral. And you see for standard weights, you have less than 1%. So it is much more difficult. Of course, beware, these kind of computations say nothing about the asymptotics, because 9 is really, or 11 is not much, not much. But what is true is that many techniques that people have developed for combinatorial Laplacians, the ones with weights 1 in vertices and edges, but if you know, Seidel switching is a standard technique to construct in the combinatorial world, isospectral graphs. Well, these do not work in the case of standard weights. Okay. So that's justification for focusing on this here. And let me now start with what is the frame. So I will start in this second part telling you which kind of graphs we have. What is a magnetic field? How do you model it? And what kind of operators we do consider. Okay. So my graphs are quite general. In this talk, they will be finite. They will be oriented, and we do allow multiple edges and loops. Yeah. So in many articles, people restrict to what is called simple graphs without multiple edges and loops, but we will allow this in complete generality. So a graph consists of vertices. A is for arcs, meaning oriented edge. And then the orientation is described in terms of an incidence relation, which is a map eating an arc and telling you who is the source and what is the sink, from where to where you go. Okay, standard. Some additional notation, you have an involution, which is just reversing the edges. And well, this induces that the two action on edges and the unoriented edge is just the quotient. Yeah, so if you want the pair of both orientations for each edge. I need a bit of notation. A, B minus, these are all oriented edges that start at B. Yeah, so this would be one example here. Okay, and the degree is just the cardinality of these edges. Yeah, so you sit on an edge, you look at all the, you sit on a vertex and you look at all the edges, all the arcs that leave that edge, that vertex. Okay, and the cardinality of this set is just the degree, the one we had there. Okay, so I was all the time speaking about magnetic fields. Think of a vector calculus course, and Maxwell's equation is the motivation. So think of a constant magnetic field through the graph, for instance. And one handy way to satisfy the Maxwell's equations, or at least one part of Maxwell's equation, is to say, well, my magnetic field comes from a magnetic potential here. So it's an exact form, if you want. In this case, EB is equal to 0 automatically, and that's the picture. You also have Green's theorem, or if you want Stokes' theorem, which tells you that if you have a magnetic field, somehow a surface here, and you have a magnetic field, and the flux of this magnetic field through the surface can be computed as a circulation of the potential along the boundary. Okay, so in graphs, a magnetic field is modeled in terms of a function alpha, which eats arcs or oriented edges and maps into essentially S1. You can take, you have some freedom here. You can take any discrete subgroup here. You can take set 4 or whatever. But let me stick to S1. So essentially the interval 0, 1, these are the values of your magnetic field, and they live on the edges of the graph, yeah, motivated by Stokes' theorem. There is a relation. If you reverse the orientation of the edge, you have to reverse the value of the magnetic potential. That's the requirement. And as in physics, the potential, as ever in physics, a potential does not fix the value of the field uniquely, but you have a certain freedom, which is called the gauge freedom, or you say that two potentials, alpha and alpha prime, are equivalent if there is a scalar function. So scalar, for me, the space discretized into vertices, and somehow the edges describe the connections between the space point, which are discrete now. So you say that the two potentials are equivalent if there is a scalar function living on vertices, such that, oh, this should be 2 pi z, such that the difference is exact, meaning that there is this function such that this difference is a dig psi. Dig psi lives on edges or on arcs, and then it's just the evaluation of the scalar function on vertices on the sink minus the value of the function on the source, yeah, delta minus, okay? And we are going to have many graphs, finite, directed, allowing multiple edges and loops. And I call this a magnetic graph, meaning you have a graph and such a function describing or modeling a discrete version of a magnetic field. Okay, so that's a literary name if you want, magnetic graph, but this is what I mean by that. Okay, so let me now go to the constructions. Yeah. Well, first of all, we want to associate Hilbert spaces. We want to construct operators on them. And we have following natural Hilbert spaces. So everything is finite here today, but we are also very much interested in infinite graphs. And there you have, of course, an N2 convergence condition. So take functions from the vertices on C, which I like to think of like zero forms of functions on the space. My space are the vertices, it's discretized now. And you have also L2 functions on the arcs, on the edges, which I like to think of as one forms if you want. And again, you have the same restriction as before. If you have the coefficient eta sub E on the with the other orientation, you have to flip the sign. Okay, so here are the scalar products. As you see, we put in the function on the vertices, we put the degree. And I told you, if you like Schrödinger operators, you can just work here with completely general weights on the vertices, and on the edges, you can just throw in a general weight. Okay. Now I'm going to give, I don't know if you have experience, this is an analysis seminar, maybe you have not so much experience on that. But when I started, this is not also my principal area of research. But when I started looking at Laplacians on the combinatorial literature, for me, it was very difficult to realize that they were self-adjoint, positive definite matrices, etc., etc. I want to give you present the Laplacians as a Laplace-Beltrami operator, a discrete version of it. So I need to define for you a map, a first order map that joins functions on the vertices with functions on the edges or on the arc. So here comes this first order operator. So G is just a magnetic graph with your magnetic potential. And then you define an outer derivative if you want mapping zero forms, functions on the vertices to one. And it's called a twisted derivative in the sense that, well, if you don't like magnetic fields, you put on alpha equals 0 and you can follow everything for the same price. Okay, but I prefer to put it this way. So it's called in the literature twisted derivative. And you eat a function on the vertices, f, and you get a function on the edges by just, as we did before, evaluating the function on the sink minus the value of the function on the source, and then you twist by the magnetic field alpha E here. Okay, so that's a first order derivative, and the Laplacian is then defined as usual. So if you have L2 of B, L2 of E, of arcs, and then you have an adjoint map here going from the functions on the arcs back to the functions on the vertices. And the Laplacian is defined as a D star D, yeah? Labeled by the parameter alpha, the value of the magnetic field. And here you have the standard formula for the Laplacian, which you will see. And if you start with this formula, it's, at least for me, not obvious that the operator is positive definite, which is trivial in this with this construction. Self-adjoint is also for free. Usually you start in, or at least if you look at the literature, you see this kind of formulas. Okay. Also very geometric, because you see that the Laplacian evaluates the function at a point and then looks at the effect on first neighbors. Yeah. So this is a first neighbor of B. And then you take a kind of mean. So it's also a very nice way of describing the operator, but some analytic properties, you don't see them immediately. So remember again, this is just the arcs here are just those arcs that start at V or leave V and end at the first neighbor, delta plus E. Okay. Now, let me go back to the magnetic field. In the literature, there are many weights and there are many operators, and you have for each of these operators tons and tons of papers and results, etc. The magnetic potential for me is really a nice way to interpolate all these operators. For instance, if alpha E is equal to 0, if you hate magnetic fields, so find them not natural for the graph, then you put alpha equals 0, and then you get, you forget about this phase here, and you get the usual standard Laplacian, which is given here. There is also what is called the signless Laplacian, for which there is a lot of literature again. Then if you put alpha E to be pi, you reverse this sign here, you have a -1 here, you take it out, and you get what is called the signless standard Laplacian. And also the signature Laplacian. There was a few years ago, a very famous pair of papers in Annals constructing expander graphs that use the so-called signature Laplacian that essentially is choosing for each edge or for each arc a -1 or a 1 here. Yeah, so this is also very important. And so you see the magnetic field interpolates all these operators, and the flowers I showed to you before are isospectral for all of these, and of course all of the magnetic Laplacians that are in between, if you want. Okay, so this is the object. This is the operator for which we want to construct isospectral graphs. Okay. Since we are still in the introduction, let me just say a few things about these operators. The Laplacian is positive self-adjoint, and you can easily bound the norm by 2. It's very, very easy. So the spectrum of these Laplacians lie between 0 and 2. So you see, contrary to the usual Laplacian on manifolds, even on metric graphs, these are all unbounded operators. So these are bounded models. Yeah, the operators are bounded, and that's convenient. So you don't have to say much. You don't have to care too much about technique. No Sobolev space, nothing. Okay, so a few more facts. So if you have H equivalent potentials, we recall the difference is exact, then the Laplacians are unitary equivalent, and so the spectra are the same. Yeah. So the gauge equivalence respects what you want. Another remark, new fact, to have a non-trivial effect on the spectrum of the magnetic field, you need that there are cycles. Yeah. So for instance, if you have a tree, if your graph is a tree, take a path graph, and you switch on a magnetic field, the Laplacian does not change at all, because you can show that any Laplacian on a tree is equivalent to 0, and so you essentially just have one Laplacian, which is the one with alpha equals 0. Yeah? So you need to have a kind of cycle, which is, on the other hand, physically quite obvious, because you need a surface to have a non-trivial flux. Okay. What else? Again, if you have no magnetic potential, then you always have 0 as in the spectrum of the Laplacian. In fact, the multiplicity of 0 is counting how many connected components the graph has. So this is a classical result in spectral graph theory, and that's why I said that the Laplacian carries the geometry of the graph. Yeah. But if you have cycles and you switch on a magnetic field, then you see that 0 is not anymore in general in the spectrum of the Laplacian. So there is really an effect on the spectrum. Yeah, and yeah. Let me now come to the. Is there any question? We are in a family, so you probably have no questions. But if you have questions on the background, what I'm saying, that's the point. Because from now on, I will start with the new parts. So this is very classical and very standard, and there are many, many more facts that I'm omitting here because I don't know.
Do all these definitions change a lot if you assume that your graph is not directed, meaning for each edge that you have, you always have the opposite one as well? or something like that. Do definitions simplify a lot, or
well,
I guess the physical meaning is lost?
No.
Or in a sense, well, at least the one pertaining to your drawing here, right?
Yes, magnetic field is sensible to orientation. You can, if you put alpha equals 0, you have the same definition. So this first order operator requires an orientation. But the nice thing is that the Laplacian is, if you are not interested in magnetic fields, then the Laplacian does not see the orientation of the graph. If you want to do this first order operator approach, then you need it. But in D star D compensates that. So you can define the Laplacian without magnetic field completely independently of the orientation. And in fact, it's an operator that is blind towards our orientation. But then you cannot pass through this first order derivative, because derivatives see orientations. If you are in an edge, and you define the derivative, this is of course noticing the orientation of the graph. But in general, if you don't want magnetic field and you only want Laplacians, you can work without orientation. And in fact, you can start with any orientation, the Laplacian does not change at all. But if you want a magnetic field, then you need to specify an orientation. Okay, so now comes the first, and for us, the most important technical tool, which is a pre-order on the class of magnetic graphs. Yeah? So you have your magnetic graph, the graph of magnetic field, the order n. And let me write the spectrum. Everything is finite, so you get a bunch of eigenvalues from 1 to n. They may be repeated, and we order them, that's very important, from the smallest, which is 0, if alpha is 0, up to the biggest, which is in any case below or equal 2. Okay. Then we are going to say that G and G prime with orders n and n prime, we say that G is spectrally smaller than G prime with shift Q. It's a long sentence, which we summarize in this symbol, G below G snake with shift Q. If the order, so how many, the order means how many edges you have. If n is beyond or equal n snake, and you can compare the kth eigenvalue of G with the k plus Q eigenvalue of G snake from 1 up to n minus Q. If Q is equal to 0, we just say this here. Yeah? G is below G snake, spectrally. This is if you want, a handy way of writing G below G snake and G snake below G with shift 1. Just means that the eigenvalues interlace. So lambda 1 is below lambda 1 snake, and lambda 1 snake is below lambda 2, which is below lambda 2 snake. So it's an interlacing of eigenvalues. Okay. And so on the set of magnetic graphs, this defines a pre-order. Yeah? So symmetry is missing, and the symmetry is missing because we have isospectral graphs. Yeah? Symmetry means that if G is below G snake and G snake is below G, if this relation would be symmetric, then the graph should be isomorphic, but they are not. Okay. So this is just defining, this relation here is just defining a pre-order in the category of graphs. Now for the construction, because I'm only interested today in the construction of isospectral graphs, I need two perturbations of the graphs, and I will try to capture the spectral effect of the perturbations. How can you perturb a graph? You can do it in many ways, but today we want to have only two of them. Yeah, because this is what I need. The first one is the vertex contraction. And if you look at the combinatorial literature, when you contract two vertices, you usually delete the loop. We are keeping the loop. Yeah. So if I contract B1 and B2, I just keep the loop here. So this edge is not deleted. Combinatorialists work in the category of simple graphs. So whenever you have a loop or a multiple edge, they try to take it away. But we are not doing it. Okay, so now the first result. What is the effect of the construction on the spectrum? So you have a magnetic graph. You select a bunch of vertices, V naught, and denote the quotient graph by G snake. Yeah? So you just glue together and keep the edges, all the vertices in uppercase V naught. Yeah? Then you know this is a proposition, not difficult to show, that G is spectrally below G snake, and G snake is spectrally below G with shift Q, and Q is just a shrinking number. So how many vertices you lose on the quotient by this gluing? So in this case, the shrinking number would be 1 because you have 3 vertices here, you have 2 here, and that's what you get. Yeah, that's a very well, it's not very difficult to prove. Yeah. Let me show you an example instead of a proof. Let me show or illustrate this relation here with the following example. A is just a graph. As you see, it's a tree. There are no cycles here. And so the eigenvalue are these dashed lines. So the horizontal line is just changing the value of the magnetic field here from 0 to 2 pi. And you see there is no change at all. So these are constant. And this dashed lines here, this is the first eigenvalue of this graph here that has a cycle, and we can put a magnetic field here in one of these edges. It's the same, it's equivalent. You can distribute the value of the magnetic field on the tree, or you can concentrate it on one. It's exactly the same because you have this gauge freedom. Yeah, and that's exactly what is written here. Yeah? So G is below G snake. So this is the eigenvalue, the first eigenvalue on the cycle, if you want, and the second eigenvalue of the initial graph is below the second eigenvalue. The first is below the second eigenvalue of the one with the cycle. Yeah, so that's what you can do with these operations. Okay, so this is the first operation. And the second one is called vertex virtualization. It's not vertex contraction. What I mean by that is, imagine that you have a Laplacian and you distinguish some vertices there and you put Dirichlet conditions on these distinguished vertices. Yeah. So here again, G is a magnetic graph. You distinguish a family of vertices and you consider the magnetic Laplacian, but you restrict them to Dirichlet conditions on V naught. So on certain vertices here, you just consider only values 0 for the functions on that. Yeah, or if you want, the virtualized, so you have the usual Laplacian, magnetic Laplacian, and then you compress it to the subspace of all L2 functions on the complement of this distinguished vertex at V naught. Yeah, and we want to call them the Laplacian just with a plus. So this is my symbol for virtualizing, and the plus comes from Riemannian geometry. So if you have a Laplacian on a compact Riemannian manifold, and you make and with boundary you may consider Dirichlet and Neumann eigenvalues, and Dirichlet eigenvalues are always dominating the Neumann eigenvalues, so are bigger if you want. And that's the justification of the plus here. Yeah, so the spectrum of the virtualized Laplacian is just the spectrum of the usual Laplacian compressed. So this is the inclusion, and iota star is just a projection onto this subspace of L2 of V. Okay, that's and now comes the next result. What is the spectral effect of virtualizing vertices? So here it comes. It's again such a kind of sandwiching we had before. G is a magnetic graph. You distinguish some vertices on which you want to consider a Dirichlet condition. Let me call Q the number of vertices where you put Dirichlet conditions. And this is the virtualized graph. And then you know that this virtualized graph lies between G and itself with shift 0 and shift Q. Okay, so again, you have a spectral shift of the eigenvalue. And well, we have considered just two operations, contracting vertices and virtualizing vertices again. But in this article last year, we did a really systematic, you can virtualize edges, you can delete edges, you can elementary perturb the graph, and here you have the effect on the spectrum. We analyze it in, well, this is 50 pages article, very systematically. But we only need these two for the construction. And now I promised you a short talk. We start a bit later. And let me now go straight to the construction, which is something you can do with kids, because it's like playing with mechano pieces. And that's exactly what I'm doing. Okay, here we go. Now comes the construction. So there are 3 steps, and you can start with any what we call building block. So here is the graph. Now it's just a path graph decorated with one multiple edge. Yeah, but any graph qualifies. Yeah, and any magnetic graph qualifies. Now with this graph here, we are going to construct what we call frames, which are the building blocks of the flowers we had in the very beginning. Yeah. So you have any building block and you take a natural number and you distinguish some vertex sets here. So the North Pole and the South Pole in this very simple example. You write the disjoint union, disjoint P, disjoint copies of the building block. And then you put them together, or you glue together all the vertices in V0. Yeah. So these are the frames. They depend on the natural number, how many copies you have. And they depend also on which vertices you want to glue after the disjoint union. So F1 is the building block. And here are the examples. So you have this building block, you choose North and South Pole as gluing vertices. And so F2 is just 2 copies of the building block glued together along the North and South Pole. So you get these underpans. And then you continue. So 3 copies of this and glued along the North and South Pole, etc. For each P, you get a frame. Okay. So this is the second step. Now comes the, well, that's important. That's important result. We need to know the spectrum, the spectra of the frames. Yeah, and that's not very difficult to compute. You have to do a bit of lifting eigenfunctions, but again, such a frame, F3, for instance, the spectrum of F3 contains a copy of the spectrum of the building block. Yeah? And then you also have the spectrum of the building block where you virtualize the North and the South Pole. Yeah? Remember, plus means strictly condition on the set V0. Yeah? And you have it with multiplicity P minus 1. So this is multi-set notation. So if one is if the number 1 is in the spectrum of G, and 1 is also in the spectrum of the virtualized G at V0, then you have to copy it twice. Yeah, so it's a multi-set. It's not a set theoretic unit. Multi-set. So multiplicities do play an important role. Okay, so you have the frames, and you know what is the spectrum of the frames. And now, how do you construct the flowers we started with today? So you have a magnetic building block, you choose some vertices in there, yeah, and then you produce these frames, yeah, the building block, the underpans, and etc. And now we want to build isospectral non-isomorphic graphs. How do you do it? Well, first of all, well, this construction goes a bit more general, and in fact, it is way more general. You don't have to take V1 in V0. But so from these gluing vertices, you distinguish a special one. Let me say B1. Then you take a partition of the natural number. So I don't know, a partition in the sense of number theory or combinatorics. So you have R equals 6, which is the example I'm going to show. And the S is the, for instance, 2, is the length of the partition. And so you can write 6 as 1 plus 5. You sum 6 as sum of 2, or 2 plus 4, or 3 plus 3. So these are 3 different partitions of 6. And here A is denoting the partition. Yeah? So A is the partition of R, meaning that A1 plus AS is equal to R. Okay. And now you have your frames, and you take your frames coming from the partition A1 up to AS, these S frames. You put them in a disjoint union and glue them along this super distinguished vertex in V node. Yeah. And well, let me illustrate in this example. This was the building block. This is F1 glued together with F5, which is this little flower here. This is A2. Sorry, A is equal to 4. It's the second partition here. So you glue together the frame F2 with the frame F4 and F3 with F3, 2 times glued together at this vertex V1. Okay. And well, these are the flowers. And here comes the theorem. That's the one I wanted to state. So you have a magnetic graph, which is a building block. You distinguish some vertex set to produce the frames. And now you distinguish one of those vertices. You have a super distinguished vertex V1 in uppercase V node. And you glue the frames along this V1, following what the partition is telling you. So if you want, it's a number theoretic property. And now you take 2 different S partitions of R. So you take 1, 5 and 2, 4 if you want. So these are the 2 different partitions. Of course, you have to start at least at 4, otherwise you don't have 2 different partitions. And then the graphs that you get by gluing the frames along what the partitions is telling to you are isospectral and not isomorphic. Yeah, so these graphs are not isomorphic. The flowers are the examples and are isospectral. And not only that, you can compute the spectrum completely. And what is in the spectrum? It's the spectrum of the building block appears once. Then you have the spectrum of the virtualized building block with Dirichlet conditions on uppercase V node. And then you also get in with multiplicity R minus S. So R is the number that is giving you the partition, and S is the length. And then you also have the spectrum of the Laplacian with Dirichlet conditions on V1 with multiplicity S minus 1. So if you believe this second part, you know that they are isospectral, because the spectrum does not depend on which kind of partitions you have. They only depend which number you are partitioning and how big, how long is the partition, and how many pieces you are breaking the number. Okay, so the spectrum of FA only depends on R and on the length of the partition of R, and not on the particular decomposition in A1, A2, A3, or B1, B2, B3, etc., etc. Okay. And so if you can count how many S partitions of R, the number R you have, you get cardinality of this number families of non-isomorphic isospectral graphs for the discrete magnetic Laplacian for any alpha. So if you change alpha, you change the spectrum. Yeah, you cannot compare alpha equals 0 with alpha equal 1, but with a fixed potential, all of these flowers are isospectral. Yeah. I'm not saying the spectrum for all alpha is the same, but the families, the construction is stable on that. And in particular, the flowers we had before are isospectral for the standard Laplacian, the signet standard, for the signature Laplacian, for all the Laplacians I explained to you. Okay. And there is in the literature one construction very similar to that, but only for the path graph and really very linear algebra proof. So not using this spectral inclusions and restricted to this path graph. Okay, and of course without magnetic field, which is really strange in the combinatorialist literature. Let me give you very briefly the idea of the proof, just a sketch of how we reason. And it's a very simple idea, which exploits the fact that you can sandwich spectrally the graphs. That's the main idea. Okay, so you have the unknowns for now is the spectrum of Fa. Yeah, you have a magnetic Laplacian there, and all the eigenvalues are unknown. But you can sandwich Fa between Fa B1 virtualized. So the gluing vertex, you put a Dirichlet condition, and that it means that you are disconnecting the two flowers, F3 and F3. Yeah. So with this equation here, and you can easily compute, knowing the spectrum of the frames, you can compute the spectrum of this virtualized Laplacian explicitly. And then what this inequality is telling you is that, so if you let me write lambda1 for the spectrum, the first eigenvalue of the Laplacian corresponding to Fa. If you look at this inequality, this is lambda 1 plus is just the Laplacian Dirichlet conditions on the gluing vertex. And then you look here and you know that the first eigenvalue of lambda 1 plus is below lambda 2 because you have shift 1. So you have an interlacing. And this is without the plus, these are the numbers you want to determine and so on. Lambda 2 plus, etc. And so this sandwiching, if you know that these two are equal, if these two are equal, then you know already lambda 2. So that's the idea. And why do you have these multiplicities? Well, because you are using, your frames are very symmetric, and this reflects on the spectrum with high multiplicity. So with this technique, you can, this sandwiching technique and the high multiplicity of the eigenvalues allows you to detect or to compute many eigenvalues of your Laplacian, but not all. And then you need a second equation, which is, you can probably use different ones. We succeeded with this one here. So you put the disjoint union of the frames, and you know the spectrum because you know the spectrum of the frame, and the disjoint union produces just multiplicity. And this is enough to determine the other. So for instance, if there is a jump between these two eigenvalues, you cannot say anything of the eigenvalue in between. And so you have certain elements of the spectrum which are not determined, but then you use another sandwiching equation. And this is exactly what you need to determine the unknown elements of the spectrum. Yeah, and let me say again, this spectrum is known because of the theorem I told you before, and this spectrum is also known explicitly. Yeah, and so in other words, what you use is you exploit that the frames are highly symmetric, and this gives you a lot of eigenvalues with high multiplicity, which allows you to determine the spectrum. And well, I also told you that graphs are not isomorphic. And the reason is, it is true that in the spectrum, you don't see the particular form of the partition, but in the degree list of the graphs, the partition appears explicitly. And since you use different partitions, so you will get in the degree list 1 and 5, or 2 and 4. And then you can, because of the construction, you can really write down the degree list, and you see that they are different because the partitions appear here, and so the graphs are non-isomorphic. Okay, so this is a very rough sketch of what how you prove this theorem. So what have we done? We have explained why these flowers are isospectral. I hope you see the frames here: F1, F5, F2, F4, F3, F3, and if you want a number theoretic object like the partition of a natural number, gives you the graphs. And we have, if you want, we have produced a factory of isospectral graphs. We have as many isospectral graphs of cardinality of PRS, which is the number of partitions of R of length S, but we have a lot of real more because any building block qualifies. So you have really tons and tons of isospectral graphs for the standard Laplacian. But of course, the interesting question is, this is of course huge, but the number of graphs here is enormous. So the interesting questions in combinatorics is, if you close your eyes and pick up two graphs, are they going to be isospectral or not? This we are not addressing here, although we had it in the beginning as a motivation. If you want to address these kind of questions, for instance, there is a theorem that tells you that of Schwenk, I think, all trees are conspectral, for instance. Well, if you want to address these questions, maybe multiple, you should restrict to simple graphs. This is my opinion, because if you allow multiple edges, then you have not the complete graphs as a kind of upper bound. But anyway, the procedure gives you really tons and tons of isospectral graphs. And for us, it was very interesting or very useful, this spectral sandwiching, if you want. We exploited it again and again and again. And in fact, well, these are the publications, but I told you this is part of a bigger question, or different questions we asked within the spectral analysis or spectral graph theory or analysis of graphs. For instance, this bracketing technique or sandwiching technique we have used to analyze infinite covering graphs and to detect spectral gaps. In fact, well, if you have a covering, the spectrum becomes much more difficult. It's an infinite graph. And we use the magnetic potential as a Floquet parameter to decompose the Laplacian, for instance. Or you can, even if a combinatorialist would say, well, you with the magnetic field are doing something which is external. You're using an external function on the graph. Still, we can answer questions of combinatorial questions like, you have a graph, when is it Hamiltonian? When does the graph has a perfect matching? These are questions of combinatorics, and we do have spectral abstractions. You compute an eigenvalue, you look if this eigenvalue is below 2, and then well, this is not for the standard Laplacian, it's for the combinatorial, which is different. Yeah, you look if otherwise almost every eigenvalue satisfies this. But you have, if you find a vector potential whose second eigenvalue of the Laplacian is below 2, then you know for sure that the graph is not Hamiltonian. This is a spectral abstraction, which is useful in some cases, or it's not matchable or has not a perfect matching. Okay, so these are other possible talks, but let me just stop here and thank you for your patience.
Thank you very much. Questions? One.
Perfect, Chair.
Please. No, yeah. So first question is, your magnetic Laplacians do have a physical interpretation. You explained it. Does your result have any physical interpretation as well?
Well, here, I mean, It depends. If you think that, forget about the magnetic field. If you think that a discrete Laplacian is modeling in a network some diffusion, which I think it does. Yeah, so you may have diffusion on a manifold, on a metric graph. A metric graph is like a graph. But, so let's put a triangle here. So here you have edges, but a metric graph is just LE. You have a length, yeah? And then you consider Laplacians, which are essentially minus second derivative along this edge. Yeah? And this is this kind of metric graph. So the edge is not just a combinatorial object, it has a length from 0 to LE. Yeah? So this is the edge. Well, these graphs are called quantum graphs, and they are a simplified model for diffusion of a manifold. And you can go one step further and discretize this and think of a discrete structure. And I do think that the discrete Laplacian models, if you have an infinite network, you can describe diffusion of particles along this discrete, jumping from one edge to the other. And then a magnetic field has a physical interpretation, of course, because you have the structure with if you think of electrons, the electrons do. You think an electron jumping from here to here, from here to there, then the magnetic field, it has an effect on electrons. So yes, you can. I'm not sure if the isospectrality has now a physical, I never thought, but maybe I can think about that. But the magnetic Laplacian, the discrete one with a magnetic field, has an obvious interpretation as a discretization of a physical object. Sure.
And I have one more, which is actually you mentioned it, but let me make sure I understood. So you think that your techniques are not going to be helpful in classifying or in finding all kinds of isospectral graphs? Because there are a lot, right? Your technique is very specific. You take advantage of the fact that you know a priori
Symmetry.
that your two candidates to be isospectral are actually built from the same building blocks, and in a very specific manner, actually.
Yes.
You do know of examples of isospectral graphs which are very different from this kind of construction.
Yes, and we do apply also the spectral sandwiching to produce. So I presented one way.
Okay.
But the spectral sandwiching allows you to show that you have isospectral graphs which are not blocks, so they are not so symmetric.
Okay.
But you can use the same technique as here to show that they are isospectral. The point is that you have no systematics. What I found very nice here is that you have a partition of a natural number as an input for constructing the flowers.
Right.
So this connection to number theory was really nice when now maybe it's not so nice anymore because you understand it, but in the beginning was one reason. But you can construct different ones. But I don't know what is the percentage.
Right.
The problem is that there were not many constructions at all in the literature.
Okay.
Really not much for the standard Laplacian, many for the combinatorial. So this was one of the, but I don't know how many, and still these are not simple in general, although you can produce simple ones if you take a path graph. But I don't know if they are many or not. I have no feeling because the complexity of graphs is beyond my understanding for me. I don't know. Thanks.
Any other question, comment?
So what about infinite graphs?
That's our next project, how to construct isospectral covenants. That's what we are tracing now. If you have, a covering, you have a group that is moving a fundamental domain, which is a finite graph, and you move it along with the group. And there, if the group is abelian or not, makes a lot of difference. If you have abelian or non-abelian coverings, because the Floquet theory, or you want to decompose your Laplacian, which is a Laplacian on an infinite graph, You decompose it as a direct integral. And if a group is not abelian, then the dual is a mess and it's more difficult. But infinite graphs is also something which we would like to do. And that's the next step, isospectral coverage. That's what we want to do.
There are no more questions. Then we thank Fernando again.